All right. Okay, so today the topic is L'Hopital's rule. L'Hopital's rule is a very convenient formula. It's very useful to calculate limits. So useful, in fact, that people that know it try to use it even when it doesn't work. So you have to be careful with that. Let's say first what it is. So recall limits of fractions. Suppose that I want to calculate the limit of something that looks like, let's say, limit when x tends to 1 of x squared plus 2 divided by 2x minus 1. All right. So you have a fraction, you have, for every value of x, you get a different number up here and down here, and you want to find out what happens with the limit. There was actually one section where we talked about rules for limits, and one of those was the fraction of a limit was essentially the limit of the fractions, was the limit of the top divided by the limit of the bottom. Let's see how that works in this case. If you just looked at the limit of the top, the limit when x tends to 1 of this thing, what do you get? You get 3, right? So the top part goes to 3. What about the bottom part? Bottom part goes to 1. Okay? So you say, well, duh, that's obvious, right? The top part goes to 3, the bottom part goes to 1. So the whole thing has to go to 3 over 1. And that's exactly how it works. The whole thing is equal to 3 because one of the rules of the limit says that the limit of the fraction is equal to the limit of the top divided by the limit of the bottom. Okay. That's the easy one, right? That's the case when you don't need L'Hopital's rule. You can evaluate it by inspection. Just look at the limit of the top, look at the limit of the bottom, and that's it. Let's do another one, a little harder. This is 0 from the right of sine of x divided by logarithm of x. Let's see, so the top part goes to 0, right? And the bottom part, logarithm of something that becomes smaller and smaller is it 0? No. If you remember the shape of the logarithm function looks like this. So when x becomes smaller and smaller, logarithm of x becomes more and more big and negative, right? So this is actually minus infinity. Okay. So you say, well, the top part goes to 0, the bottom part goes to minus infinity. So you're dividing something that is very small by something that is very large and negative. So by inspection, you should be able to figure out that this is actually 0. Okay? Something that gets very small divided by something that gets very big and negative. Now, I don't mean to say that the bottom part is equal to minus infinity. It's just a notation to say the bottom part goes to minus infinity. So when I write 0 over minus infinity, I mean the top part goes to 0, the bottom part goes to minus infinity. It's not that they're actually equal to that. It's a little bit of what we call an abuse of notation, but it's okay. In this case, we can do that. And this is what's called a determinate form. Basically because you can say 0 over infinity is equal to 0, we know what it converges to. But what about, let's look at another limit, the limit when x goes to 1 of logarithm of x divided by x minus 1. Okay, so in that case, the top part goes to, what is logarithm of 1? Logarithm of 1 is 1? 0, that's right. In fact, a lot of you guys in the midterm, you were forgetting this. There was a lot of places where you could simplify, instead of logarithm of 1, write equal to 0, and that simplified a lot of things. Many of you didn't realize that at the time. So the logarithm of 1 is 0. And this thing goes to 0. What about the bottom part? The bottom part goes towards 0 too. Okay, so this thing goes to 0 over 0. And then what do? Is that equal to 1? Does it cancel out and gives 1? Not necessarily, right? Something that is very tiny on the top divided by something that's very tiny on the bottom does not necessarily give 1. It could be 5. Or it could be that the bottom part gets tiny faster, and so the whole thing goes to infinity. Any of those things can happen. So this is actually unknown. Okay? It's what we call a undeterminate form. So 0 over 0 is an indeterminate form because you cannot determine the limit by just looking at the fraction. In other words, by inspection. Okay, so then what? Well, that's where L'Hopital's rule comes to the rescue. Let me write it down. So L'Hopital's rule, suppose that f of x and g of x are differentiable near the function, near the point x equal to a. Now, if this fraction f of x over g of x is of indeterminate form, okay, so 0 over 0 we said is an indeterminate form. Can anybody tell me some other indeterminate form? In other words, some fraction where you say, I really cannot tell what this converges to because it doesn't, just doesn't tell you just from looking at the fraction. Any other example? What about, yes? Excellent, infinity over infinity. If something goes to infinity on the top and the bottom, then you don't really know what the whole thing converges to. There's another example. For example, in this case, we had a minus infinity in here. What about infinity divided by minus infinity? Is that also indeterminate? It's also indeterminate. So in fact, you could have plus or minus infinity on the top and on the bottom. And they're all indeterminate forms. So you could have plus or minus infinity on the top, plus or minus infinity on the bottom. Those are really the two indeterminate forms, 0 over 0 and infinity over infinity, give or take plus or minus. Then the limit when x goes to a of f of x divided by g of x, that's the thing that we want to compute, is actually equal to the limit, and you write the same thing as before, x goes to a, but the difference is you write f prime of x divided by g prime of x. So it's a weird thing. You just, instead of derivating, instead of the fraction as it was before, you write the derivative on the top, derivative on the bottom. Notice that's not the same as derivating the fraction, right? It's not the quotient rule. You're derivating the top divided by derivating the bottom. And as a matter of fact, that gives you the right answer. There's one more fine print, which is that this thing over here should have an actual limit. Okay? If this thing doesn't have an actual limit, then it's not equal to because it's nothing. It's not a well-defined number. But suppose, assuming that this limit exists, you can just calculate it and it's equal to that. Okay, so let me give you an example. Same example as before. Limit when x tends to 1 of, what was it, log x divided by x plus 1, x minus 1. Once again, this thing goes to 0. The thing on the bottom goes to 0. So we say, by L'Hopital's rule, this is L'Hopital's, is equal to the limit when x tends to 1. And then we're going to derivate the top. That's 1 over x. And we're going to derivate the bottom. That's 1. Okay. Now, at that point, you can look at this expression. 1 over x divided by 1. That's just 1 over x, right? And when x goes to 1, that converges to what? Just 1, right? I mean, if you want to think about it, this is always 1. And this top part goes to 1. So the whole thing goes to 1. That's it. Let's see, let's do another example. So, for example, the limit when x goes to 0 plus of the logarithm of x divided by 1 over x squared. Okay, what's that? Well, the top part goes to, remember, what happens with the logarithm function when x becomes very, very small? Minus infinity, right? And the bottom part goes to, actually goes to infinity, right? When x becomes really, really tiny and positive, 1 over x squared becomes very, very big. Okay, so we can apply L'Hopital's rule. And this is equal to the limit when x goes to 0 plus of 1 over x, that's the derivative of logarithm, divided by the derivative of 1 over x squared. What's that? Well, think about it. 1 over x squared is the same thing as x to the minus 2. So this is minus 2 x to the minus 3. All right. So what's that? Is equal to the limit when x goes to 0 plus. And then I'm just going to simplify this a little bit. I'm going to write the 1 over x here. And the 1 divided by minus 2 I'm going to write over there. And this thing of dividing by 1 over 3 x to the 3 is the same thing as multiplying by the inverse of this thing, which is x to the 3. So it's the same thing as multiplying by x to the 3. Okay? And this thing is the limit of (1 over minus 2) multiplied by x squared. Right? And that is just 0. Okay, so as you can see, L'Hopital's rule, well, I mean, I guess we didn't show it, but L'Hopital's rule also works for one-sided limits. And it also works for a is equal to infinity. What was a again? A is the limit. A is, sorry, the point at which you calculate the limit. So limit when x goes to a, it could be, for example, limit when x goes to infinity. Yeah, it would also work too. What other notes? Let's see. Okay, I think that's it. Do you guys have any questions about L'Hopital's rule so far? No questions? Okay. So let's do a couple more examples. Let's do the limit when x goes to 0 of x squared divided by 1 minus cosine x. Okay, let's see. This goes to 0. So what is the limit of the top? Is 0. What about the limit of the bottom? Well, cosine of 0 is 1, right? Okay. By the way, once again, in the exam there was a bunch of questions where it was just very basic trigonometry. Cosine of pi, for example. Cosine of pi is actually minus 1. That's right. A few of you forgot that, and you wrote cosine of pi be equal to 1, but it's actually minus 1. Okay, 1 minus cosine of 0 is 0, and in fact this whole thing goes towards 0. Okay, so what do? It's 0 over 0, it's an indeterminate form. So by L'Hopital's rule, this is equal to the limit when x goes to 0 of 2x. On the top we derivate, and on the bottom we derivate and we get minus the derivative of cosine, which is minus sine, so that's just sine of x. What's that? Okay, so the minus becomes, the minus stays there. The derivative of cosine is minus sine, right? So you get sine. Okay? Okay, so great. So now what? Well, let's see. The top part now goes to 0, and the bottom part goes to 0. So we still have an indeterminate form. Does that mean we made a mistake? No. You just keep going. Okay? So at that point we can use L'Hopital's rule once more. The idea is that things get a little bit simplified every time you do it. So for example, we went from x squared to 2x, which is a little bit easier, and now it's just sine of x instead of 1 minus cosine. So you just be patient, verify that you still have an indeterminate form, and apply L'Hopital's rule once more. X goes to 0 of, on the top part we get 2, on the bottom part we get cosine of x. Okay, and what do we have there?
2 over 1.
That's right, 2 over 1. Is that an indeterminate form? No. So the answer is 2. Who would have thought, right? You just look at this thing, you say, well, there's no way that's going to convert to 2, but that's what it is. Okay, so let me give you an example, another example. Do you guys remember this first example I gave you? Let's see. Here, this very first limit here. Let me write it down again. The limit when x goes to 1 of x to the 2 plus 2 divided by 2x minus 1. Okay? Notice that the top part goes to 3, the bottom part goes to 1. Right? So suppose you just see that limit and you say, oh, I'm a master of L'Hopital's rule. I can do L'Hopital's rule anytime. L'Hopital's rule is easy. So let's take L'Hopital's rule. Okay? So you derivate the top, you derivate the bottom. And you get 2x on the top, and on the bottom you say 2. Okay? Now, this is the limit when x goes to 1. So that this goes to 1, this goes to 2, this goes to 2. So the whole thing goes to 1. Right? Okay, but what happens? What happens here? What is the actual answer? 3, right? So how do we get that 1 is equal to 3? How is that possible? Can anybody explain to me? Or is what happened here? Yes? That's exactly right. L'Hopital's rule only applies when you have an indeterminate form. And this is not an indeterminate form because the top part goes to 3, the bottom part goes to 1. So this is not the same as doing that. So one way to remember this is if you don't need it, you can't use it. Which is a very elegant rule. You can only use this tool when you actually need it. In fact, those cases, 0 over 0, infinity over infinity, those were the scary cases. Remember, in the beginning of the quarter, we were talking about those as like the scary ones, the ones that we didn't know how to deal with. So now those are the ones that we know how to deal with. It's interesting, no? All right. So let's see. I already gave you a bunch of examples of L'Hopital's rule in action, at least for fractions. So now it turns out we can use L'Hopital's rule for some other situations. For example, you can use L'Hopital's rule for indeterminate products. Indeterminate product is a product of two things, one of which becomes really, really small, another one becomes really, really big. So let's see. So given a limit of a product, one can use L'Hopital's rule by rearranging to form a fraction. So it's not that L'Hopital's rule is more general. It's not like there's a L'Hopital's rule for product. Okay? It's more that you have a product and you can rearrange it or manipulate it algebraically so that you get a fraction and then use L'Hopital's rule. For example, suppose we want to calculate the limit when x goes to 0 of x times logarithm of x. Okay, and this actually should be 0 plus. Why do I write 0 plus and not just 0? Yes? Or at negative, for negative x, right? What doesn't exist for negative x again? What doesn't exist for negative x? The logarithm, that's right. Once again, here's our little graph of the logarithm function. You can see that logarithm is only defined for positive x. It's not defined for negative x. So that's why we only look at the limit when x goes to 0 plus of this thing, because the logarithm is not defined for negative x. Okay, so you look at this product, you say, well, when x becomes very, very small, this thing goes to 0, and the logarithm function goes to minus infinity. So you see there's some kind of struggle between those two terms. One of them becomes really tiny, the other one becomes really big and negative. So the question is, who wins out? Is the one that becomes smaller becomes really, really, really tiny, so that even if you divide it by some large negative number, it's still really, really tiny? Or does the other term win out? So is the 0 a tinier 0 than the infinity is a large infinity? You know, I don't know if that makes sense to ask it that way, but you see there is a struggle between those two terms. So what you do is you have to rephrase it or rearrange so that you get a fraction and you can apply L'Hopital's rule. What do you think? How can we rearrange this term? Yes? That's exactly right. Thank you. So we write this as the logarithm of x divided by 1 over x. It's a cool trick, right? Now it looks like a fraction. It's the same as before, but the top part goes to minus infinity, and the bottom part goes to infinity, which is a indeterminate form. It's an indeterminate form. Okay, so at that point we can use L'Hopital's rule. So L'Hopital's rule, it's the limit when x goes to 0 plus of, well, the derivative of logarithm of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. Okay? At that point, we can rearrange a little bit, right? That expression there, you can rearrange it a little bit as you want. In this case, we can write minus 1 over x multiplied by x squared, right? So dividing by 1 over x squared is the same thing as multiplying by x squared. 1 over x times x squared. And this thing is equal to, well, this is equal to minus x when x goes to 0 plus, that's 0, right? Great. All right, so there you go. Questions? All right, so now we can also do indeterminate sums. So an indeterminate sum could be something like this, something that goes to infinity minus something that goes to infinity too. Yes, sir?
What if you had a fraction like 4 over 0? Is that indeterminate?
So the question is, what if you have a fraction, the top goes to 4, the bottom goes to 0? That's a very good question. It's actually not indeterminate. You can figure out by inspection what it is. Generally, it's infinity, but there's a caveat. So you're thinking about something that goes, on the top something goes to 4, on the bottom something goes to 0. Here, let's do this here on the side. So limit of, let's say when x goes to 0, of 4 cosine x divided by sine of x. Let me be a little bit more precise. Yeah, okay. Limit when x goes to 0 plus of 4 cosine of x divided by sine of x. All right, what happens to the top? The top goes to 4, okay? And the bottom goes to 0, right? But you can be a little bit more precise than that, because you see 4 over 0, you still don't really know what it is, because what it means is that the bottom part goes to 4 and the bottom part becomes a really, really tiny number. Okay, but here's the problem. If the bottom is a really, really tiny positive number, then the whole thing goes to infinity. If the bottom is a really tiny negative number, the whole thing goes to minus infinity, right? So you have to keep track in this case of whether it's a positive small number or a negative small number. And the way you write this is, in this case, it's a positive small number. When x becomes small and positive, then sine of x is a very, very small and positive number. So you're dividing something that it becomes close to 4 by some really tiny positive number. And that is 4 divided by 0 plus, that's infinity. Okay? If this was a very small and negative number, you would write 0 minus. And then you would write 4 over 0 minus, that's minus infinity. Okay? Thanks for asking. That's also not a determinate form, not an indeterminate form. It's no need for L'Hopital. No need for L'Hopital's rule. Okay? All right, so now let's go back and talk about indeterminate forms. Let's see, so suppose you have the limit when x goes to pi over 2 minus of the secant x minus the tangent of x. Okay, so let's see. You guys remember what the tangent function looks like? If this is pi halves, the tangent function looks like this. So the tangent function becomes very, very large at pi over 2. So this thing is actually converted into infinity. Just that part, that part of the sum. What about secant? Well, secant is actually 1 over cosine, right? What happens with cosine at pi over 2? What is cosine of pi over 2? It's 0, right? So that means that secant becomes very, very big and negative. Sorry, big and positive. All right, so that's infinity. So now we have a function that goes to infinity minus another function that goes to infinity. So the question is, which one wins over? Does this thing necessarily go to 0? Do they cancel out? Well, no. That one of the two functions can grow faster than the other, in which case the limit could well be infinity or minus infinity, right? So what do we do? Any ideas? Same trick as before. We have to rearrange so that we get a fraction, and we can apply L'Hopital's rule. All right. So let's see. How do we rearrange this thing? That's absolutely right, Kendrick. So that we're going to rearrange this so that it looks like 1 over cosine of x minus sine of x over cosine of x. And you can see now this is actually a fraction. You can write it down as a fraction. One minus sine of x divided by cosine of x. And sure enough, the sine of pi over 2 is what? Is 1, right? Okay, so 1 minus 1, the top part goes to 0. And the bottom part goes to 0. So it's part of the beauty of this thing is that when you have an indeterminate sum and you rearrange it as a fraction, it becomes an indeterminate fraction. It doesn't need to happen, but it usually is the case. It's like some kind of cosmic elegance of mathematics, if you will, that indeterminate things are like kind of go together. All right, so the top part goes to 0, the bottom part goes to 0, so we can use L'Hopital's rule, and this is equal to the limit when x goes to pi over 2 minus of of what? Negative cosine divided by negative sine. Okay. Now, cosine of x, when x goes to pi over 2, that actually goes to 0. And sine of x, when x goes to pi over 2, actually goes to 1. Is this an indeterminate form? What do you think? This is not an indeterminate form. We actually know what this is because it's 0 over 1 is actually 0. In this case, there's no need. When you're dividing 0 over 1, you don't need to do 0 plus or minus. It's just 0. If the 0 had been on the bottom, we would have had to be more careful and find out if that 0 is quote-unquote a positive 0 or a negative 0, meaning that the very small number, whether it's a very small positive number or a very small negative number. But in this case, there's no need to do that. And we know the limit is 0. Okay, we still have a few minutes left. I'm going to give you another form, and then if we have time, we're going to prove at least one part of L'Hopital's rule. L'Hopital's rule is a very powerful rule. It can be applied in all kinds of different cases. So the proof, basically the proof has to be made as a different proof for each case. So we're really only dealing with one case, probably the easiest one, but it's still pretty cool proof. So let's see if we have to do it, if we have time to do it. So finally, indeterminate powers. So suppose that you have a limit where, let's see, a limit where the bottom part goes to 0 and the top part, the exponent, also goes to 0. So that's indeterminate because something to the 0 in principle goes to 1, right? If you have something and you do it to the 0, right, it becomes closer and closer to 1. But if the number itself on the bottom is becoming smaller and smaller, you would think it actually should go to 0, right? 0 to the something is 0, but anything to the 0 is 1, so one of the two has to win over. And so you have an indeterminate form. So let's calculate the limit when x tends to 0 plus of x to the x. Once again, the bottom part goes to 0. The top part also goes to 0, so we have an indeterminate form, and we don't know what it is. Okay, so here's the idea. Once again, you have to rephrase or rearrange so that you get something that you can use L'Hopital's rule on. In this case, we're going to define a function y of x equal to x to the x. Let's take the logarithm on both sides. What is the logarithm of y? So logarithm of y is the log of x to the x, and that's x times log of x. So can we compute the limit when x goes to 0 of that? What's that? It's an indeterminate product, right? Not only that, but we actually already did it. Let's see, where is it? Here. It's right here. The limit when x goes to 0 plus of x times logarithm of x, it's an indeterminate product. We already saw how to do it. We rearranged this expression to get a fraction, and then we use L'Hopital's rule, and you get that the answer is 0. Okay? So we just did that. We already know. So the limit when x goes to 0 plus of logarithm of y of x is equal to 0. So now what? Now what do we do? Well, you can take basically the exponent e to the x on both sides, if you will. Let's see, so limit when x goes to 0 plus of y of x is equal to limit when x goes to 0 plus of e to the logarithm of y of x. Okay? So y is always e to the logarithm of y, and because the function e is continuous, we can write this as e to the limit when x goes to 0 plus of natural log of y of x. But we already know that that thing is 0. So this is e to the 0, which is 1. Okay, so this one's a little harder. But anyway, it's actually not that hard. Just think about it. If you have a power, you do, for example, you have a power like this. You write it as e to the logarithm of that expression. You calculate the limit of that, and then you go back. Yes, Arden?
Why did you just stop at 0 when you got 0?
Because that was the wrong limit. The limit that we calculated was the limit of x logarithm of x, which is the logarithm of y. But we want to find the limit of y. Okay? Thanks. So Arden was asking, why didn't we just stop here at this point? All right. Great. We have 5 minutes. So let's do prove-L'Hopital's rule for the case 0 over 0. So suppose that limit when x tends to 0 or to a, f of x is equal to 0, and the limit when x tends to a of g of x is equal to 0. So okay, so f prime of x divided by g prime of x okay, now that thing is actually, you can describe this as the derivative let's see, f of x minus f of a divided by x minus a, and the bottom is also the derivative g of x minus g of a divided by x minus a. So basically what I'm writing is this thing is the limit, this thing is the derivative of f at a divided by the derivative of g at a. Okay? So this limit, you can cancel out the top and the bottom. Okay? Also, assuming that these functions are continuous, if the derivatives are well defined, the functions better be continuous. So we also have that f of a is equal to 0. So this is f of x minus f of a divided by g of x minus g of a. Okay, but f of a is equal to 0, and g of a is equal to 0 also by continuity, right? The functions are continuous at a, so f of a has to be equal to 0 and g of a has to be equal to 0. So this thing is equal to the limit when x tends to a of f of x divided by g of x. So here you can see in reverse of sorts that the limit when x goes to a of f of x divided by g of x is actually equal to the limit of x tends to a of f prime divided by g prime. That's probably the easiest case. The other cases are a little harder, but it's the same kind of thing. All right, thanks.